Hi everyone, welcome to the continuation of our ninth lecture. This lecture is only for the calc-based physics students, and what I'm going to do in this lecture is I'm going to revisit the RC, the RL, and the LC circuit that we studied during our electricity and magnetism series, and derive those exponential decay formulas that I gave you previously, but without actually proving them. Okay, but to derive those equations from more fundamental principles, that's going to require calculus. And so this is only for the calc-based physics students, okay? If you're wondering what kind of questions I can ask about this subject, you'll see those kinds of questions both on the assignment that I'll give you and also during the tutorials when I solve some sample problems. But in this lecture, just try to understand the principles that are involved. Okay, the lecture that you're going to see was again recorded last year at this time, but I had to replace the introduction with this introduction. Okay, our first circuit that we're going to look at in greater depth, and this is the RC circuit. So this is a circuit that's made up of a resistor and a capacitor in series. Okay, so let me just remind you, because this going back to before magnetism, let me remind you a little bit about how that circuit worked. And I've got the circuit drawn right here. Okay, now there was actually, if you go back to the lecture where I first introduced this, there was actually a battery, or there was a switch where you could have the battery in the circuit or not in the circuit. And so the battery, when it was in the circuit, would charge up the capacitor here. And then when you switch the switch and took the battery out of the circuit, it would then the capacitor would then discharge. Okay, but the capacitor was always forced to discharge through this resistor, and so the discharging wasn't instantaneous. It would take some time, and that's what this formula is right here. This formula basically says if the capacitor begins with an initial charge of Q naught, when you close the circuit so that the capacitor can begin to discharge through the resistor, then the charge on the capacitor will decrease over time. It'll decrease over time exponentially like this. And the exponential has this time constant tau, and tau is equal to RC, okay? And basically, the bigger the resistor is, the longer it'll take to discharge, and also the bigger the capacitor is, the longer it'll take to discharge, okay? Now, there were really two forms to this formula. One was when the battery was in the circuit and it was charging up, and then this is the one where it's charging down. We don't have to look at both of them. The whole point of doing this is to just have a deeper understanding into how these circuits work, and I think it's sufficient to just look at the discharging for all of them. We're going to look at three different circuits, okay? So let's start off with the RC here, and uh, we have this circuit, and remember that when you have a circuit and there's potential drops in the circuit, if you add up all the potential drops, they have to equal the potential that's delivered by the battery. Okay, now if you look at the circuit, there's no battery in it, and that means that as you go around the circuit, you're going to have a potential drop across the resistor here. Okay, and we're going to call that VR, and then you're going to have a potential drop across the capacitor, and we will call that VC. And the potential drop across the resistor plus the potential drop across the capacitor has to equal the potential given by the battery. There is no battery, so those two potentials have to add up to zero. Okay, and that gives us our first formula. Okay, now at this point you might wonder, well, if there's no battery, what's giving the push? What's delivering the energy for the current that's going to flow through this circuit? And the answer is that any energy that's in this circuit is actually coming from the capacitor. Now, I didn't derive this during that previous lecture, and I'm not going to derive it now, but you can actually show that the energy in a capacitor is given by this formula. I actually wrote it in two different ways here. You can write it as Q squared over 2 times the capacitance, okay? And that's equal to the amount of energy that's in the capacitor. Remember, you got to charge a capacitor up, you've got to apply a potential, and there's going to be this current flowing on there, and as the current flows on there, you're doing work, electrical work, to get that charge onto the capacitor, and so there's an energy stored up. Okay, so that's one way to look at the energy. Another way is 1/2 CV squared, where V again is the voltage across the capacitor. Okay, and we're going to use both of these forms later, so I'm introducing them right now. I'm giving them to you without derivation, so let me at least show you that the units work out correctly. You expect the units to be joules. And so if you take the units of Q squared divided by 2C, that's just the units of Q squared divided by the units of C. 2, of course, doesn't have any units. And the units of charge is is Coulomb. Okay, so this the Q squared will give you a Coulomb squared, and the units of capacitance are farads. All right, and so remember that a farad is a measure of capacitance, and capacitance is how much charge you get per volt. So it's a Coulomb per volt, and so you can replace that farad on the bottom there by a Coulomb divided by a volt. Okay, and simplifying that, it gives you a basically a Coulomb times a volt. All right, but don't forget that a volt, it's a measure of potential, and potential is how much energy per unit charge. So a volt is a joule per coulomb. So you can replace that volt by joule per coulomb. The coulombs cancel and you wind up with joules. And so you can see that the units do work out. Okay, so I actually just did the units of this one right here. But if you look at the units of that one there, by the way, the two are just related to one another by the definition of capacitance anyhow. But if you analyze the units of this one, you'll see that it also works out to be joules. Okay, so what is this energy? This is the energy that is stored in a capacitor because there's a charge on it, and that's the energy that's going to push the current through that through that circuit. Okay, so you don't need a battery. The energy is coming from not from the battery because there isn't one. It's coming from the capacitor. Okay, now in that equation 1, maybe I better just quickly remind you of equation 1. So here's equation 1. It basically says, look, there's a potential drop across the resistor plus a potential drop across the capacitor. That has to equal 0 because there's no battery in the system. Great, so now let's take a look at each one of these potentials and see how we can rewrite them. So the potential across the resistor, for that we could just use Ohm's law. Okay, so the potential across the resistor is just going to equal the current through the resistor times the resistance. All right, and similarly, you can, for the potential drop across the capacitor, you can use the definition of capacitance. Now, the definition of capacitance was C. The capacitance is equal to Q divided by V. That's how much charge you get per volt. But, just rearranging that equation, you can write that the VC is going to equal Q over C. Okay, so the potential across the capacitor is the charge on the capacitor divided by its capacitance. Okay, so substituting both of those into equation 1, we get the following. Okay, so this one, that was VR, okay, and using Ohm's law, it's IR now. And this one was VC, and using the definition of capacitance, it's now Q over C. And let's now remember that current and charge are related to one another. Okay, so remember that current is how much charge flows per unit time. In fact, in the lecture, I wrote it as delta Q over delta T. Okay, but we can write this as an instantaneous rate, and so it's dQ by dt. In other words, the current is the first derivative of the charge. Okay, so there you can see that I is equal to dq over dt, and we can substitute that now for I in the equation, and now you can see that you have an equation where you can solve for Q. Okay, it's a differential equation, meaning it's not just plain old Q's in there. It's a there's a dq by dt, but you can solve this equation, and the way I'm going to do it is I'm going to isolate dq by dt on one side. All right, and there it is. Well, not yet, but there it is there. But in doing that, I had RC there, and remember RC I'm going to define as tau, and so there's tau, and then rearranging it, so I have dq by dt on one side. I have that dq by dt is going to equal -1 over tau times q. Okay, so I put it in this form because now it's very easy to see what a solution to this equation looks like. So basically, this equation says something like this. Look, if you have some function for q, okay, function of time, so you have this function of time for q, and you differentiate it, what are you going to get? Well, you're going to get q back again, but with some constant in front, minus 1 over tau. Okay, so again, we're going to, the solution to equation 3 is actually a function, q of t. And how does it work? Well, if you differentiate q with respect to t, you're going to get q back with this constant minus t over tau in front. Okay, now without going into some theory about how differential equations are solved, I'm going to just give you the solution. The solution is q is equal to q naught e to the minus t over tau. In other words, it's the equation for the discharge of a capacitor in an RC circuit. Okay, and to show that, it's pretty easy to show that this here does in fact satisfy equation 3. If we take q and we differentiate it with respect to time, well, there's the q naught, but q naught is a constant, so that just comes right out in front of the differentiation operator. Okay, and then inside the differentiation operator, we have e to the minus t over tau. And we're going to use the chain rule here. The first thing we're going to do is we're going to differentiate this with respect, this whole thing in the square brackets here. We're going to differentiate it with respect to the exponent. And e to the x, when you differentiate e to the x, you just get e to the x back. Or in this case, if you want to think of it as e to the t, if you take e to the t and differentiate it with respect to t, you just get e to the t back. Okay, so that's kind of neat because that's sort of what a natural log is. When you differentiate the natural log with respect to the argument, you get the exact same function back. Okay, and so when you differentiate this, you will get, first you differentiate with respect to the entire argument. Remember, we're using the chain rule. So you differentiate with respect to the entire argument. And that just means you get e to the minus t over tau back again. Okay, but then you have to differentiate e to the minus t over tau with respect to t. And that just gives you minus t over tau like that. And so you can bring that in front. All right. And then finally you say, oh, I've got back my q naught e to the minus t over tau. But that's just q. Okay, and so if you just replace, well, here it is again, so just look at that right there. Oops, okay, just look at this right here. Q is q naught e to the minus t over tau. So if I just recognize that q naught is equal to e to the minus t over tau, I could just replace that all with q. And what did I just show? I just showed that dq by dt is equal to minus t over tau q. Okay, so what does this prove? This proves that this differential equation here is solved by that exponential decay. Okay, now I didn't just show you this for the mathematics. I wanted to show you this for a couple of reasons. And the basic reason is this idea that if you've got a bunch of electronic components in a circuit, all right, go way back to equation number 1 here, you can add up their potentials like this, and that's going to equal 0. Now, we actually did that when we analyzed our resistors in series and parallel. We did this. But there, we did it statically so that, the current wasn't changing over time. But here, this is a more interesting problem. It's still true that the sum of the potential drops has got to equal to the potential of the battery, one of Kirchhoff's laws, okay? It's still true, but it isn't true statically, meaning, that it doesn't change over time. It's true even if these quantities change over time, okay? And do they change over time? Sure they do, because VR, the voltage across the resistor, it changes as IR, okay? And I changes over time, okay? And does the potential across the capacitor, VC, does that change over time? Sure, because the charge of the capacitor changes over time, okay? So both of those potentials are changing, but they're changing in such a way that one compensates for the other, okay? And that's exactly what this equation is saying here, okay? And then the second reason I wanted to show you this is that it shows you how the charge is related to the current. Current really is the rate at which charge changes, okay? So it's kind of like a velocity. Remember, you have position when we were doing one-dimensional kinematics. You have a position, and the first derivative of the position with respect to time was the velocity, dx by dt. It's the same thing here. You have q, which is the charge, and dq by dt, that's your current, okay? So the current is kind of like a velocity in analogy, all right? Well, putting that all together, and massaging this a little bit, you get this differential equation. Now, we've seen differential equations earlier in the course. I introduced them for the wave equation, but there it was a second order differential equation. I actually saw it last semester too with simple harmonic motion. There it was a second order differential equation. That is, you differentiate it twice with respect to time. Here you only differentiate once with respect to time. And if you differentiate only once with respect to time, what solves this is actually an exponential. So not a sine function, which we'll see a little bit later in the lecture, but it's an exponential. Okay, and so there you go. There's the proof that the charge in an RC circuit, a resistor and capacitor in series, an RC circuit, the charge on that capacitor when it's discharging will exponentially decay over time according to this formula here. Okay. All right, well that's it for the RC circuit. Let's look at the RL circuit, okay? And by the way, this is why I waited to this point in the course to introduce this, because I just did the RC circuit, but now I'm going to do the RL circuit, and that requires magnetism, okay? And I'm also going to do the an LC circuit, okay? That's going to be the last circuit, okay? So for the RL circuit, there we had that the current through the resistor or through the inductor was going to exponentially decay over time like this. So you had some initial current, all right, and then that current would decay over time. So I of t is the current at any given time t. I naught is the initial current, and it exponentially decays over time, okay? And again, there's this time constant, but now the time constant is equal to L over R, okay? The time constant for an RC circuit was RC, but the time constant for an RL circuit is L divided by R. Okay, so we're going to prove this equation here. Well, what is this RL circuit? It's basically this. Okay, we have a resistor and an inductor in series. Okay, and let me just remind you what an inductor does. It's a little bit, it's probably the most subtle of all of our electronic devices. It basically resists changes in current. Okay, so if there's a current going through it, it really doesn't want that current to change. And the way it resists that change in current is because it builds up a magnetic field that tries to maintain that current. Okay, but it's not going to be able to maintain it because that resistor there is going to dissipate the energy over time. Okay, so proceeding as we did above, there's a potential drop across the resistor, and we'll call that VR, and there's going to be a potential drop across the inductor, and we'll call that VL. Okay, and again, there's no battery, and so those two potential drops, when you add them up together, they have to equal 0. Okay, we'll call that equation 4. All right, and now you might ask the question, in the RC circuit, the thing that provided the energy was the capacitor. It can't be the resistor. The resistor dissipates energy as heat. Okay, it does joule heating, but so the energy had to come from the capacitor. But here in the RL circuit, what's delivering the energy? And the answer is obvious. It has to be the inductor. Okay, and so there's an energy in the inductor, and the energy in the inductor is given by 1/2 Li squared. Okay, so again, I'm not proving that, but there it is. Okay, and I'm going to show you at least that the units work out. So the units here have to be the units of inductance, and the units of current squared. Okay, the units of inductance is a Henry, but a Henry can be written as an ohm second. Okay, and the units of current are amps, but they're squared, so it's an amp squared. Okay, and so we get an ohm second times an amp squared. Now, what's an ohm? An ohm resistance out of Ohm's law, it's a volt per amp. Okay, so an ohm is an volt per amp. So we can write the ohm as V over A. And so one of the amps will cancel out. Okay, and then this reduces to a volt amp second. All right, but now you remember, isn't an amp just a coulomb per second? And so you can write amp as coulomb per second, right? 1 coulomb flowing by per second, that's what you mean by an amp. Okay, and so an amp is, you can take out that amp and write it as a coulomb second. But then if you multiply the amp times the second, the seconds will cancel, and all you get left is a coulomb. So now this is reduced to a volt times a coulomb here, like that. Okay, but don't forget what a volt is. A volt measure of potential. It's how many joules per coulomb. Okay, how many joules of energy for every coulomb of charge that you have. And so a volt is a joule per coulomb. If you put that in there, the coulombs will cancel and it reduces to a joule as you expected. Okay, so yeah, I mean, I didn't prove the 1/2 in front, but the Li squared, at least that you know is some kind of an energy. Okay, so it's E is equal to 1/2 Li squared. All right, so now let's go back to equation 4. So just to remind you, because I jumped around a bit, what equation 4 is saying. So it's the potential drop across the resistor plus the potential drop across the inductor has to be equal to 0. The potential drop across the resistor, we just use Ohm's law, it's IR. The potential drop across the inductor, we use the definition of inductance. Okay, so if you remember how inductance is defined, that's this L here. It's defined by this formula, actually. The potential drop across the inductor is equal to the inductance multiplied by the rate at which the current changes. Okay, if there is no change of current across an inductor, there is no induced potential. Okay, it's when the current tries to change in the inductor resists that. But if the current does change in the inductor, that's when a potential is set up. Okay, and so there it is. There's the formula for the potential across the inductor. If we put both of those into equation 4 above, we have, here's our VR, Ohm's law, and here's VL, which is the inductance. Okay, and now let's just rearrange this and write the di by dt all on one side. And so over here you have di by dt is equal to minus R over L times I. Okay, and remember that tau, the time constant for an RL circuit, is L over R, like that. And so we can write this as di by dt is equal to minus 1 over tau I. Okay, this equation 5 has the exact same structure as the differential equation above in terms of dq by dt. Okay, and so it's pretty obvious that it's going to be solved by I. I is a function of time. Okay, so I didn't write the time dependence there, but I is going to change over time, is going to equal the original time, that's the original current, that's the current at t equals 0, multiplied by the exponential decay. Okay, and if you differentiate this in exactly the same way as above, I naught is a constant, it comes out in front. We differentiate the e to the minus t over tau. First we differentiate with respect to the entire argument, which just gives us back the e to the minus t over tau, because exponentials, when you differentiate an Euler's constant to its exponent, okay, you just get Euler's constant to that exponent back again. But then when you differentiate the minus t over tau with respect to t, you're going to get minus 1 over tau. Okay, like that. And that just reduces to this, and you identify I naught e to the minus t over tau as I, the time-dependent current, and you just get this back again. So di by dt is equal to 1 over tau, minus 1 over tau times I. I dropped the minus in there, guys. I apologize. There should be a minus right there. And that is exactly equation number 5. Okay, and so what I basically showed you is that equation number 5, okay, is solved by that exponential decay. Okay, great. It's so the RC circuit and the RL circuit, they're both homologous to one another. They're similar. It's just that for the RC circuit, you're looking at the exponential decay of the charge, whereas for the RL circuit, you're looking at the exponential decay of the current. Okay. Okay, now the last circuit is probably the most interesting one. And if you remember, this is the LC circuit, okay? And the LC circuit actually oscillates. And just to remind you of the physics of that, you have like you could start off by either charging up the capacitor, or getting some current going through the inductor, one or the other. Just imagine that the capacitor is charged up, and so the capacitor is charged up. Suppose that the top plate is positive; it's going to push a current through the inductor to the negative plate. Well, eventually the capacitor will discharge, and it won't have any capacitance on the top or the bottom. Oh, sorry, it won't have any charge on the top or the bottom. Okay. But at that point, there will be a current through the inductor. And the inductor says, oh, I'm going to keep this current going. And so it's not like, the capacitor just discharges and it stops. No. The inductor keeps the current going, and then it makes the bottom plate positive, and the top plate negative. But at some point, the capacitor says, oh, that's enough, and then the process reverses. The bottom plate is positive. It forces a current through the inductor to the negative plate on top, and then eventually the capacitor discharges, and there's no net charge on the top or bottom. But again, now there is a current through the inductor, and that current keeps going because the inductor is going to keep it going, but the current now is going in the other direction. And so it goes one way and charges the capacitor one way, and then it goes the other way and it charges the capacitor the other way, and it does this back and forth over time, and there's a characteristic frequency for that. Okay, so how do we do this one? Same thing. You've got a potential drop across the capacitor, you've got a potential drop across the inductor. Those two potential drops must equal 0, like that. Okay, now before I actually solve this, it's not that hard to solve. It's really interesting because it's almost identical to the simple harmonic oscillator. So the energy in the circuit, it's going to be a combination of the energy. So I wrote these two energies above, but now I'm going to bring them together. There's the energy in the capacitor, and that's the 1/2 CV squared. VC, the voltage across the capacitor. Okay, so it's 1/2 C times the voltage across the capacitor squared plus 1/2 Li squared. Okay, so this is the total energy, but there's no resistor in the circuit, so that total energy had better be conserved. And if you take a look at that, you'll see that it's 1/2 CV squared plus 1/2 Li squared. And if you think about this a minute, that looks an awful lot like the total energy of a simple harmonic oscillator. Okay, where you had here, let me see if I can get them both in place. Yeah, where here you have, the energy going back and forth between potential and kinetic, as the oscillator oscillates back and forth. At the end points, it's all potential energy. In the middle, it's all kinetic energy. Well, it's the same thing here. Okay, the energy oscillates back and forth, but not really between kinetic and potential. Okay, unless you want to think of the current as some kind of a kinetic energy. I guess you could think of it that way. But it oscillates back and forth between all the energy being in the capacitor and all the energy being in the inductor. Okay, and that's what causes the oscillation here. We're going to plug back into this formula in a minute. You'll see that that energy is in fact constant. Okay, over time. All right, and again, you expect that energy to be constant because there's no resistor. And if there's no resistor in the circuit, we're assuming ideal wires so that the wires are not going to contribute any kind of resistance, okay? But if there's no resistor in the circuit, then where's the energy going to go? Well, the energy doesn't get dissipated as heat. The energy can only slosh back and forth between the capacitor and the inductor, okay? And all right, so the potential drop across the capacitor is Q over C. We saw that above, same formula here. The potential drop across the inductor is L di by dt. We saw that above, same formula here. And we're going to use one more formula, and that is that the current is dq by dt. Okay, and so in this formula for the potential drop across the inductor, we can take the current there and replace that current with its definition in terms of the charge, okay, on the capacitor. And so we have a double derivative here. We're going to differentiate the current, but the current itself is dq by dt. And so you can write that the potential drop across the inductor is the inductance times the second derivative of dq by dt. Okay, and I think you can already see where this is going to go, because if you have a double derivative like this, you get sinusoidal motion. The single derivative will give you the exponential decay. We just saw that in the previous two examples. Okay, but the second derivative will give you sinusoidal motion. Okay, so let's substitute for VL above, and let's also substitute for VC. Whoops. Sorry, sometimes I lose the screen. Okay, let's substitute for VL above and VC above. Okay, and the equation looks like this. Okay, so we have no battery, so no potential. Here's VC, the potential across the capacitor, and here's VL, the potential across the inductor, but now written as, not di by dt, but in terms of the charge, which is d2q by dt squared. Okay, we're solving for that d2q by dt squared, so let's bring that to the other side. And now our equation looks like this. Okay, and we've got negative 1 over LC. Let me write that 1 over LC. Let me write that as omega squared. Okay, in other words, omega is going to equal 1 over the square root of LC, like that. And so then this equation here can be written as d2q by dt squared is equal to minus omega squared q, equation 10. Okay, you've seen this before. This is sinusoidal motion. Okay, and so you ask the question, what function do I put in for q such that this equation is solved? And the answer is a cosine or sine. You could do either one, but we've usually done cosines. That's what we did for simple harmonic motion and for waves, so we'll do that here. So the time-dependent charge on the capacitor is going to equal some maximum charge, we'll call that Q naught, times the cosine of omega t. All right, and what's that omega? It's the angular frequency, but now the angular frequency is equal to 1 over the square root of LC, okay? Where L is in the inductance and C is the capacitance. So you could see that the inductance and the capacitance together set the frequency at which this circuit oscillates back and forth, all right? Well, just to remind you, we've done this a few times, but just to remind you, if I take this Q as a function of time and differentiate it once, dq by dt, that is the current. Okay, so wherever you see I, that is dq by dt. Well, when you differentiate the cosine, you get the sine, you get negative the sine, but we have to use the chain rule. Okay, so the q naught just goes along for the ride. Okay, when we differentiate the sine with respect to the entire argument, we're going to get negative sine, so there's the negative sine. But then when you differentiate the argument, omega t, with respect to t, you just get omega, and so you get an extra omega in front. Okay, so this is the chain rule. Remember, first you differentiate cosine with respect to the argument omega t, multiplied by differentiate omega t with respect to t, and that's why you get that extra omega out in front. Okay, now we need the second derivative, so we need di by dt, which is the same as d2q by dt squared. And if you differentiate this again, well, if you differentiate the sine, you get a cosine. All right, no negative, so that negative from before just carries along. Okay, the q naught from before carries along, one of the omegas carries along, but you get another omega from the chain rule, because when you differentiate sine with respect to the entire argument, you're going to get cosine with respect to the entire argument, but then you have to multiply that by differentiate omega t with respect to t, and you get another extra omega there. But now you recognize that q naught cosine omega t, that's exactly just q. That is the time variation of the charge. Okay, so you can replace q naught cosine omega t by just q, and basically you've got d2q by dt squared is equal to minus omega squared q. That is exactly the equation we were trying to solve. So all of that was just to show you that q naught cosine omega t, when you plug it into 10, works. Okay, if you try to plug in some other function here for q naught, it wouldn't work. Okay, the only function that's going to solve 10 is going to be either the cosine or the sine. Okay, or some linear composition of the two, but it's good enough. Okay, so this is as expected. All right, now let's end off by showing that the energy is actually conserved here. Okay, because we have two things. We have We have two functions. We have q as a function of time, but we also have I now as a function of time. Okay, so we can say how the charge on the capacitor varies with time, but we also can say how the current through the inductor varies as a function of time. So go back to that equation 7, which was the energy, 1/2 CV squared, where V is the potential across the capacitor, so 1/2 C VC squared plus 1/2 Li squared, like that. And here we don't really have VC above, but we can rewrite VC in terms of Q using the definition of the capacitance. Okay, so VC is just Q over C, like that, and this reduces to this formula right here, 1 over 2C Q squared plus 1 over 1/2 Li squared. Okay, but for Q, we have that. That's that Q naught cosine omega t. Okay, so if we plug in Q, we plug in for Q naught cosine omega t, we're going to get Q naught squared cosine squared omega t. And for I, we also have a formula, okay? And that is this one right here, okay? Because I is the first derivative of Q with respect to time. It's minus omega Q naught sine omega t. So down here, for I, we're going to substitute, this is the stuff in the square brackets here, we're going to substitute for I minus omega Q naught sine omega t. Okay, and just distribute the squaring over all the factors in there. Okay, the negative sign goes away, and you're going to get 1/2 L. Oh, let me just put it down a little bit more. Okay, you're going to get 1/2 L. That omega will give you omega squared. That Q naught will give you Q naught squared. Sine omega t will give you sine squared omega t. Okay, like that. All right, but remember, we have a definition for omega. Omega is equal to 1 over the square root of LC. Okay, well, this is omega squared, so that's just 1 over LC. Sorry. Okay, and so we can write that L omega squared is L times 1 over LC, which is just 1 over C. And so this piece right here, oh, I'm sorry, guys. This piece right here, this L omega squared, for L omega squared, we could just replace C like that. And we get a Q naught squared over 2C here, and we get a Q naught squared over 2C there, which we can factor out in front. Okay, so there's a Q naught squared over 2C. That's that factor there, and it's also that factor right there. There's a cosine squared and a sine squared. That's all that's left over. And if you remember your trig identities, cosine squared of an angle plus sine squared of an angle, what's that equal to? 1. Okay, so even though the cosine varies in time and the sine varies in time, together, cosine squared plus the sine squared don't vary. They're constant, equal to 1. And so the energy is a constant, Q naught squared over 2C. Okay, so the energy is conserved. What's the point? Well, I'm trying to show you a complete parallel with simple harmonic motion. So again, in simple harmonic motion, you have the energy going between potential energies, purely potential energy at the endpoints, and purely kinetic energy in the middle. So it goes between kinetic and potential, back and forth like that. And if there's no damping, that'll go on forever. This circuit does the exact same thing. Okay, only here, go way back up to the circuit. The energy is at one extreme, at one point in time, it's all inside the capacitor, and there's no current in the inductor. Okay, and so the energy could be all in the capacitor. But then as the capacitor discharges, some of that energy starts to move over to the inductor. Okay, eventually there is no charge on the capacitor at all, so there's no energy at the capacitor at all. All the energy is as current going through the inductor. Okay, and so the energy is sloshed to the other end. Okay, and then the inductor eventually charges up the capacitor, and then there's no current in the inductor, so there's no energy in the inductor, and all the energy is back into the capacitor, and the process just continues. So the energy keeps sloshing back and forth between capacitor, inductor, capacitor, inductor, capacitor, inductor, forever. Okay, and it oscillates with, well, this is the angular frequency. Okay, but this is the angular frequency here, 1 over the square root of LC. All right, but if you divide by 2 pi, you'll get the linear frequency, and that's what you would actually measure in the lab. Okay, this is a radio. This is the simplest example of a radio. In this circuit, there is no antenna or anything like that, but you could easily just attach, like a wire off of any end point here. And then when radio waves come by, which are electromagnetic waves, okay, so they're a combination of electricity and magnetism, the electric waves are oscillating. What are they going to do? They're going to, those electric waves that are oscillating, they're going to cause the electrons in the antenna to oscillate at some frequency. Now suppose the frequency at which the electrons in the antenna are oscillating is the same frequency at which the LC circuit oscillates, then you're going to get a resonance. basically meaning, the electrons are going to push, and then, it's kind of like pushing a child on a swing. Every time you push a little bit more, push a little bit more, push a little bit more, and it's going to build up, and, it's going to build up enough that you can actually, siphon a little bit of that energy off and, run something like, I don't know, a speaker off of that. Okay, so there you go. This is basically the simplest possible example of a radio receiver. All right, guys, that's it. So just quick summary. We looked at RC circuits. They exponentially decay. We looked at RL circuits. They exponentially decay. And we looked at these LC circuits, and they oscillate over time. Okay, and I showed that from the differential equations that arise from the sum of the potentials in around the loop. All right, thank you.